Sciences Part 3. Okay, so everything you learned is obvious, becomes less and less obvious as you begin to study the universe. Okay, so we are focusing on natural sciences, and although it seems like a very strict discipline that doesn't have a lot of leeway for questioning, we've already looked at some of the things that kind of are suspicious about the natural sciences. So basic process in the natural sciences, when you have a hypothesis, you test it. But we're going to look at some biases that could come into that. The first one would be the confirmation bias, right? We've talked about that before. We talked about it in the human sciences, that we tend to confirm things to ourselves. Okay, so the idea of confirmation bias essentially says that we always tend to look for evidence to back up our own hypotheses. So if we have this hypothesis that gravity is making this remote fall to the ground, and we start doing tests on it, we will tend to always sort of be very excited about tests that confirm our hypothesis and tend to ignore any tests that might disprove our hypothesis. So for example, say you did a test that you said, you know what, all Virgos are shy. All Virgos are shy. So every time you come across a shy Virgo, you'll be like, aha, look, another example of a shy Virgo. So you will be constantly trying to confirm your own hypothesis. Meanwhile, you might also ignore these really outgoing Virgos that come up to you. Or you might ignore these shy people of other astrological signs. Okay? That's the confirmation bias, that we are always trying to confirm kind of our own hypotheses. So it creeps into science. It's hard to get over that kind of bias or that kind of filter. Okay? So this also relates to looking at the data of your experiment. So say this is the results of your experiment. Okay? What would you call result D? What's a word you could use to describe it? An outlier, right? So generally, if we're using an experiment and we're like, okay, this looks good, looks like what I expected. Oh, but D, it's an outlier. Sometimes we tend to dismiss that outlier and go, you know what, I probably screwed up the experiment on D. I probably messed up. But what if B was also an outlier? What if F was also an outlier? How many outliers should you have before you say, you know what, the experiment's no good? What do you think?
No, it's just, did the morning class already go through this?
Part of it, yeah, part of it. Yeah.
Yeah.
Like one more slide, yeah. So how many do you think? Cash, didn't you have a formula for this? Well, that's the question.
1.5 times the interquartile range.
And is that universal? Where did you learn that formula? In math. Do the scientists use it? Did you use it in chemistry? Do you use it in biology? Do you use it in physics? Are you sure?
I'm sure.
I don't know. I don't know if I believe you guys. Because sometimes they'll, well, sure. What do I know, right? It's again that difference, like, at what point do we say, you know what, it's no longer an outlier, it's a mistake, it's not confirming our hypothesis. And scientists will tend to perform a bias on that, and they will tend to go, you know what, actually it isn't an outlier. D isn't an outlier, it's on the line of best fit, it's there, it's close enough, right? That kind of stuff does actually happen in scientific sort of studies. Not often, but it does happen, okay? Okay, the second thing that is something to think about is assumptions or background assumptions that scientists might have, okay? So here's the simple one, and by the way, this is where the morning class stopped. At the time of Copernicus and Galileo, they were basing their science on a generally agreed upon theory that fixed stars that didn't move around in the sky were relatively close to the Earth, and that they used these fixed stars to perform calculations, okay? And this is known as the parallax effect, right? So that they were using these to do calculations. But no one was able to observe this phenomenon, okay? Until the 19th century. And then they corrected it and they realized, you know what, these fixed stars are not at all close to the Earth. They're actually very, very far away from the Earth, which was the assumption that they were all going on when they did their calculations. So they were going under a false assumption at that point. And that's something that has happened in science quite a bit. That sometimes the assumptions we make, which is what the background and the basis of our calculations are, might in fact be false. Okay? As well, you can come up with many different hypotheses. That was the graph activity you guys did. What is the cause of this thermometer to act the way it is? Some of them are consistent. They are consistently seeming to be good hypotheses. And it might be impossible to disprove any of them. And that's kind of, I think that you guys really did a good job on trying to do that in the last activity. Okay? Now, as humans, we have within us something called a principle of simplicity. This is often described as Occam's razor. Has anyone heard that expression before? Occam's razor is a philosophical position that when given two things, choose the simpler one. We tend to remove the fat or cut away with the razor all this sort of extra stuff and just stick to the basic principle there. And we have that within us, that we like simple things. For example, let's say your math teacher said, here's a way to solve this equation. Here's another way to solve this equation. And out of the two of them, this one is simpler. Chances are, as humans, we would choose the simpler one based on this simplicity principle. That humans tend to like things that have a simpler sort of design to them. But that's not really a reason to choose it. It doesn't necessarily prove that the simpler equation is better just because it's simpler. It may be a better solution, but the fact that it's simpler is not a reason to choose it, okay? There's no real logic behind choosing simpler things over more complex things just based on the fact that they're simpler, okay? And so that tends to be a bit of a bias, that we tend to gravitate towards the simpler solution, when we might be ignoring the harder one, and the harder one might actually be the more correct one, okay? The other thing, too, is even though it's not generally thought of that way, the sciences have an aesthetic value to them. Okay, let's be honest. How many of you have ever had a teacher who got so excited about a math equation they described it as beautiful, or physics or something like that? I myself, and Jesse in the back can contest to this. In computer science, I sometimes get super excited about code. And I go, oh, look at this, this beautiful, this code, look at that beautiful code. You may have even heard me say that, okay? But that doesn't make sense necessarily. We shouldn't necessarily be assigning aesthetic values and then preferring a certain equation over another equation just because it looks prettier. But that's a bias. That's something that we as humans, we like simple things, and as humans, we like pretty things. That's built into us, and as a result, it affects the way we look at things. Yes?
When you say like that's a beautiful equation, are you referring to what it looks like, or are you referring to like the math, or referring to like how it works out perfectly?
You're right, right. So it could be this one. It could be the simplicity factor there. And those things tend to overlap as well, right? So we're using words and they could have different contexts. But what I'm saying in this whole thing is that that could affect a choice you make in the natural sciences. We don't tend to think that way. We tend to think that natural sciences has kind of eliminated all that stuff. But there's still some, certainly less, but there is some amount of that, okay? For example, Copernicus was convinced that planets must follow a circular orbit around the sun. And his reason was that the circle is a perfect mathematical geometrical figure. Now, they don't have a circular orbit. They have an elliptical orbit. But Copernicus was convinced purely on the fact that the circle is more mathematically correct. That's not a reason. That's certainly an assumption. That's certainly his bias towards the circle object. But it's not a good reason to choose the circle over the ellipse, okay? It's that, again, those biases coming in and affecting things even at the level of scientists like Copernicus, okay? Okay. Induction. Who remembers what induction is? Or inductive reasoning? From a bigger to a smaller, or from a smaller to a bigger? Okay, how about if I put it this way, from observed to unobserved, or from unobserved to observed? Okay, so the inductive reasoning, or the process of induction, is moving from the observed to the unobserved. The example I always use is, this door handle will open this door. And if I go to another classroom in this school, its door handle will open a door. So I'm going to make a jump in logic and say, you know what? All door handles will open doors. For example, in Zimbabwe right now, there's a door with a door handle on it. And even though I'm never, ever in my life probably going to go to Zimbabwe, that door handle will open the door. That's inductive reasoning, right? I'm jumping from the the observed instance of me opening the door to the unobserved instance of the door. In this example, I'm going to mention metals, okay? So as a scientist, you heat a metal, and it expands as you heat it. And then you grab another metal, and you heat it, and it expands. And then another metal. At what point can you make a jump in logic and say, all metals expand when heated? Do you have to test all the metals? More accurately, can you test all the metals? And even more accurately, do you even know what all the metals are? Okay? Because would you not say that you've heard people say that? All metals expand when heated. Did that mean they tested them all? Are you guys confident that someone has tested every metal on Earth?
Yeah.
No, because we might not be aware of certain.
Yeah, but all the metal we know.
All the metals we know.
But he didn't
Okay.
say all the metals we know.
Well, no, I'm glad you mentioned that, because maybe built into the statement, all metals expand when heated, is the assumption that we're only talking about metals we know, that we're only talking about the planet Earth, because maybe there's a metal on another planet, right, that we haven't encountered. So, and we're also talking about all the metals that we know and that we're aware of, right? But do you think everyone takes that statement that way? When I say all metals expand? When everyone hears me say that, do you think everyone makes the assumptions that you guys did? That they're, well, Wax must mean all the metals that we know, and he must mean all the metals on Earth.
No, because I didn't.
Right. So some people take that statement and interpret it different ways. But that is an inductive piece of reasoning. That making that jump in logic from the observed to the unobserved. All metals expand when heated. And this again raises questions. Like, how many metals should we test before you can do that? Right? How many thermometers work before you say all thermometers work? Right? There is no rule. Maybe you guys do have a formula. You had that formula about outliers. Cash, do you have a formula about this one? How many tests do you have to make before you can say all metals expand when heated? How many metals should you test? 5 metals. How about as a percentage of metals in total? 90? You don't have a formula for that one? Come on. He's rattled. The Leafs lost again last night. All right.
Sorry, buddy.
Again, from a philosophical perspective, you could certainly expand the scope of this discussion. We could say, well, what do we mean by metals? Jaja already mentioned that. Are we just talking about Earth, or are we talking about the universe as a whole? Like, the second we start expanding the scope philosophically, of course, the statement starts to break down, right? That's where TOK gets to be a pain, right? Where you're getting too philosophical there, okay? So we are, like, for example, it's said that astronomers estimate that there are 10 times as many stars in the night, or stars in the universe, as there are grains of sand in all the world's deserts and beaches. Now, let that sink in for a minute. Think about all the beaches and all the deserts in the world and all the grains of sand. Count them, multiply that by 10, and then that's how many stars are in the universe. It's a number so big it's almost impossible to even grasp. And then each of those stars could have planets and stuff like that in them, okay? We don't tend to be able to actually use our human brains to observe those kinds of massive amounts, right? So to say that all metals accounts for that as well, that giant piece of the universe, is a pretty bold statement. So it is got a lot of assumption built into it, that we're talking about just the metals we know, just on the planet Earth, and just the ones that we detect as humans, okay? So this is where philosophy and practicality tend to clash a little bit, because I can even see some of your eyes glazing over right now. Come on, Wax, just let it go. All metals expand when heated. And that's good that sometimes you get to that position, that you go, you know what? Let's stop questioning this, and let's just get on with the business of science, okay? There's a dilemma here, right? A dilemma of empiricism. Like, do we just take science at its strictest? Do we always question every single thing about science? Or do we just make these assumptions and go on with the business of doing a test so I can actually build a good metal to be used on aircraft carriers or something like that? Yes?
I think we ask more questions and kind of like question you know, like in science class, like in middle school or elementary school, you're like, why? And then as you get older, you kind of like, maybe you don't care or whatever, but you just kind of tend to just take it at face value.
Do you see this as a growing curve? Do you think when you're in university, you will question professors less?
Well, I think as a little kid, you're always like, well, why?
Yeah.
That's your main
No,
question.
I accept your premise. I think you got that a good premise there.
And I've had a lot of teachers actually, in a nice way, tell me to shut up and stop asking. So I think that also affects it a little bit.
Okay, just one sec.